then I think we are going to get started with today's talk. So welcome everyone to join our talk today, and we are very honored to have Antonino from Italy, from the image processing laboratory. Sorry, my pronunciation is not really good, but from the University of Catania. Yeah, so it's really happy to have him today here in person. And he, so basically, Antonino has already done a lot of research on egocentric vision, and he was part of the starting from the very beginning, the Epic Kitchen dataset, and then the Ego40 dataset consortium, and also the Ego-Esco40 consortium, apart from a lot of other dataset that study procedure, action, understanding, and industrial settings. So it's really I think we are going to learn a lot of state-of-the-art egocentric vision related research projects from him. And quoting his own words, his research investigates how intelligent systems can perceive, understand, and anticipate human actions and interaction directly from an embodied egocentric viewpoint to enable assistive technologies, wearable devices, and that provide direct support to users. So I think we're going to also learn something about that. So without further ado, the floor is yours. Thank you.
Right, thank you so much, and thank you for being here. Thank you for inviting me. And I'll start by saying that, well, let's first check if this works, but we kind of live in exciting times, especially if what you do every day is working at a computer. We're getting used to, rather than writing a report, you write a prompt, you get what you want in a matter of minutes, while instead writing the report requires you hours. And this is, of course, thanks to AI tools based on large language models, which are kind of doing a little bit of a revolution. I mean, if you have been using these tools recently, you're probably also familiar with the frustration of writing a prompt, getting a result which is not exactly what you want, then tweaking your prompt, and maybe going like that in circles. And finally, since you want to get the job done, you just, settle for a suboptimal result. This is probably, what everybody's experienced nowadays. And the reason why this is happening is not that these models are not powerful, because they are super powerful. The problem is that they are masters in a world that is the digital world, is a world that we created around them for probably a couple of decades now. But it's very different from the world in which the things we care about happen. And there is the physical world. Our goals, our expectations, our values, they happen in a different world, which speaks a different language. So no wonder that we're lost in translations. And who's going to translate between these two worlds? It happens to be us. So we are kind of trapped in between these two worlds. There is the physical world, where the things we care about happen. And then the digital world, where we understand we can accomplish a lot, but we need to translate, to constantly translate our context from one world to another. And I think at the moment, it is a major bottleneck of this kind of algorithms that can do a lot of things in the digital world, but they tend to be less useful in the physical one. And of course, it doesn't have to be that way. And I think an answer to try to address this kind of gap is quite straightforward, is to put the person again in the center. One way to do it is to equip the person with wearable devices and start observing what they do from their point of view, and using this as a window for AI to get perception, to perceive the world the way we perceive the world. And from this video, you see that you get a lot of information about what the person is doing, maybe also what's their diet, or even what's their layout or their kitchen, just by looking at the world from their own point of view. And once you have that, you can craft a lot of applications that can bring real value without asking the user to translate whatever they're doing and they're seeing in a language that is not their native language. And this idea of putting the person in the center and letting algorithms perceive the world from the point of view is not new. There have been seminal works starting from the 80s, and if you fast forward now in the present, we know that there is commercial interest in these. There are a lot of devices that are trying to get somewhere there. And also, there have been a lot of efforts by the community, which has provided data sets such as Epic Kitchens, Ego4D, Ego-Esco4D, and these are a huge consortia of tens of universities. And also, a community has gathered around these efforts with workshops and challenges organized every year at conferences. So I mean, the landscape is rich. Also, if you happen to be at CVPR this year, I think next week, something like that, we're organizing the third edition of the EgoVis workshop, and we're celebrating 10 years of workshops in egocentric vision under different names, but still, I mean, the same community. And this is, of course, exciting, but at the same time, we're not wearing these devices. This revolution of immediate contextual help is not kind of happening. So I think this begs the question, what is missing? What is missing from this picture? What is separating us from, what is separating the big results that we are getting from the outcome that we want to achieve, from this kind of seamless access to AI and computation? And I think, so my personal view around that is that we have not been, while we have been solving some problems, we have not been thinking of a framework for collaborative AI. And I think that to get there, we need to address three main challenges. And the rest of the talk is going to be framed around these three main challenges. So I think the first challenge is to sense the world in a way that is more coherent with an agent that has to live in the physical world and in an always-on setting. And this is what I call cognitive economy. And then we need to be able to ground perception into external knowledge. We cannot just assume that the model will contain all the knowledge of the world. And then we need to understand how to assist the user, how to intervene optimally in the life of the user to empower them rather than overwhelm them. And to start with the first challenge, I think there are two things that matter in a cognitive economy. So the ability to perceive the world in an always-on fashion. One is efficient sensing, and the other one is memory. And these two things are interlinked. If we think about efficient perception, we have been operating under the assumption that computation will scale up eventually. Like we have been building algorithms and models that are super, they are super big, and we have been saying the hardware will catch up. Especially for people working in wearable devices, this is something that we have been saying for a while. I remember us saying in workshops, "Oh, the battery is not there yet. It's not big enough." But actually, this is very different from the reality that we see if we look at living beings. We evolved to have a brain that is reasonably small and that consumes a reasonably small amount of energy. So we have not been scaling up. Instead, we are kind of scaled down to a form factor that allows us to be efficient in the way we move. And one way to do it is through efficient sensing. So efficient multimodal sensing is part of the way, it is one of the strategies by which we save a lot of energy. So if you think about it, let's say that you are having a conversation in a, relatively silent environment, not like this one. So probably in that case, you don't need to use all your senses to have that conversation. You just need to use your ears. But if you're having a conversation like this, or at a crowded bar, you probably instinctively use other senses as well. So you maybe also do lips reading. So this is something we do all the time. We try to save energy. We tune all the sensors only if we need, only if we have to. And instead, the algorithms that we have been using tend to use everything that is available at the same time. And I think this goes against the idea of having something that needs to be always on in a world that has physical constraints. So where your weights, your mass is going to be anyway limited. We have been investigating this thing in a recent work where we try to understand if we can build systems that can do this efficient sensing to understand what's going on from an egocentric video stream in an always-on fashion. So the task that we considered here was temporal action segmentation as a proxy task, where you have to classify each frame according to the action. And egocentric vision is particularly well suited for this, because it's easy to collect a wider range of modalities. So for instance, if you use devices such as AR glasses, you automatically get audio, you get RGB, you get eye gaze, or if you want high-resolution crop around the region the person is looking at. You get monochrome cameras, which are mainly designed for SLAM, but they also happen to be more, to use less energy than RGB cameras, and you get also IMU. And the idea is that if you leverage all these modalities, maybe you can learn how to how to turn sensors on and off in order to save energy. Because maybe you start perceiving what the person is doing, and maybe at some point the person is starting to do something that is repetitive, like wiping the counter, and you can turn video off entirely and monitor this kind of action only using IMU or audio, and then maybe you hear the beep from the microwave, and so you know that you need to turn the video on to understand what's happening. So that's the idea. Can we create this kind of systems? So at this stage, what we did was we thought of a general architecture where you have some kind of policy. It can be a network or it can be something fixed. We explore different things. You have a policy that using a memory, using a hidden state from a past step, tries to understand whether it's good to turn sensors on and off, also considering the amount of energy that each sensor is going to consume, and forwards this kind of representation that gets from these observations to a downstream model that performs a downstream task, such as temporal action segmentation. And then you have two loss functions, and you want to optimize both the policy and the downstream model by minimizing the cost function and also the task function. So this is the general idea. And some notation that we use is that this policy is going to predict some vectors that are 0, 1 in M modality that tells you if you have to turn things on and off. So if ATM is equal to 1, the sensor M is active. And then what we do is, okay, this fancy formula just tells us that we do 0 order hold. So if we are turning a modality off, we have a buffer of the last thing that modality has been seeing, and we're using that because it's the closest thing to what we should be observing. And this, of course, is the temporal action segmentation model. So in order to evaluate the systems, you need to be aware not only of the performance, but also the amount of energy. So we wanted a model that was, close enough to hardware. This is still, largely a theoretical model. It's not a simulation in hardware. But what you need to take care of when you compute energy is the energy that you spend in capturing the signal, turning the sensor on, the energy that you use in computing the features, and then in moving features from one part of the memory to the other. So with these terms, we compute the energy, and which are the three terms that I was talking about. And then we benchmark 4 main classes of policies. So the first one, of course, is frame rate. If I lower the frame rate and always sense all the modalities, then I'm going to save energy. The other one is a greedy policy, where you just sense all modalities at the same time for all the frames, and you have a budget per second, and when you are done with your budget, you just turn the thing on, and then you turn every modality off, and then you turn it on again when you have a new budget. So the budget resets every second. And then a random policy, where you always sense something, but you randomly subsample the modalities that you're sensing. And then there are learned policy. There's been some work in this direction, not on always-on system, but on algorithms that can segment trimmed video. And we try to adapt these models that are usually based on LSTMs or something that has a memory from the past to this task to see, where we stand in terms of state of the art. And in order to evaluate, we consider 2 different budgets. So we look at hardware, and we come up with two budgets, which are also aligned to other works in the literature. 20 milliwatts, and this is aligned to a device such as Ray-Ban Meta glasses, like very lightweight devices, and 2.8 watts, like a larger device such as Apple Vision Pro. We show that with these 2 budgets, you can run an algorithm like this for maybe 8 hours. So we want to be that kind of long range. And we evaluate with these 2 different budgets. Then we repurpose existing data, which is EgoX4D, CMU NIC, and Captain Cook 4D. We relabel them so that they are consistent, because EgoX4D has not been designed for temporal action segmentation, but more for key step recognition from trimmed clips. And we create a benchmark that is multimodal. Each data set has different modalities. EgoX4D is the richest one, with RGB, audio, and IMU, and monochrome cameras, and then also gaze. And the other data sets are smaller and have different modalities. And then we did some experiments. So here are some preliminary experiments, which are mainly baselines. And what happens, so the trends that we see is that if you exhaustively process all the sensors, so on the x-axis you have the energy, and on the y-axis you have the accuracy, you are on the top right corner, so you are consuming a lot of energy so this is a logarithmic scale, so this means this is significantly larger than the other budget. So this is 2.8 watts and this is 11 watts, about 11 watts. So you are consuming a lot of energy, but not with a big improvement in terms of performance. And then simply reducing the frame rate, which is this curve that you see here, already gives you a reasonable trade-off. We are not doing anything fancy. A greedy policy, like turning things off when you're out of budget, works surprisingly well for lower budgets, but not for larger budgets. And interestingly, the random policies have a good profile. So just randomly catching things is already smarter than just sensing everything at all time. And interestingly, we did our best to adapt these policies that have been studying for other tasks, and their profiles, they're not very satisfying. So I think there is still a lot of work to do in this sense. But this is preliminary work. We get the benchmark set up, and now we're gonna explore what we can get there. But I think this is one way to be efficient and aware of the physical constraint that you have in the real world. The other things that is linked to this idea of efficient sensing is memory. And memory is very important. It's something we probably cannot think of real intelligence without memory. So think about trying to accomplish a task without any memory of what you did 1 second ago. So that would be impossible, and that would not be intelligence. So you may be very good at computing things, but if you don't have consistency over time, this is not gonna be, you're not gonna achieve much. Instead, when you have memory, of course, you act in a consistent way and you achieve more. And you also save a lot of energy because you don't have to recompute everything of the scene, and you can just focus on one thing at a time. And this idea of memory has been explored recently in egocentric vision since, I would say, Ego4D, where there was a benchmark on episodic memory. And a couple of works have been exploring memory with large language models. And the idea here is that you let the large language model watch video, and then at some point you ask a question about something that happened in the video, and if the large language model can answer, then that means that it has a memory of what happens. Of course, this is very, limited because large language models, the way they work, they don't have a proper memory. They have a cache of what happened in the past. But anyway, they are a general purpose tool to try to answer the question, does current AI has some form of memory, and how does it remember things about the past? But the problem with the current data sets and the current benchmarks is that they don't measure memory the way we measure memory in humans, the way we think about memory. So we try to go towards that with a recent work where we propose EgoStream. EgoStream is a benchmark where that is based over other existing data sets. We try to reorganize all the questions that you have in these data sets in a way that they are consistent with the way that we measure memory in humans, so that we can ask questions such as, what is the trade-off for reducing the budget, or what is the trade-off for using an architecture rather than another on the quality of the things that you are going to memorize. And the idea is that you have a video, and usually these videos have an evidence window that has been marked in some way. So this is a window in the video where the thing that you are going to ask a question about happens. So you care about this thing. And then what we do is that we label what we call an answer validity window. So we let humans watch the video and mark the first moment in which your question is not valid anymore. So for instance, if I ask, how many oven trays did I take from the trolley? I watch the video and I mark all the part of the video in which the person is not taking any trolleys from the video, so that I know that that answer is still valid in this answer validity window. And then the first thing that we thought is we can ask the same question multiple times. Rather than asking it only once when the evidence happened, I can ask it at different temporal instant after the evidence within the answer validity window. And this is something that is usually done in psychological tests to check for how long people retain information after they learn some fact. And the second thing is that we try to categorize questions in these different categories of memory, whether they are about fine-grained details, events, so the gist of events, or temporal orderings, or spatial relationships between objects, or if they are about social relationships, or causal relationships, or they are prospectives, so about something that you need to remember, that you need to plan for the future. So we categorize all the questions in these categories, and we also consider all these recall regimes where we ask questions right after the evidence, 5 seconds in between 0 and 5 seconds, 5 and 30 seconds, and so we have instant, short, mid, long, and ultra long. And this is, I mean, is roughly aligned to what you find in psychology literature, but there is not a scale, a standard scale, and it's also kind of application aligned, because we can imagine an application that needs to be able to understand what happens a short while ago and what happened maybe at the beginning of your day. And so basically what we do is that we check inside the answer validity window and we ask the same question multiple times. And the other thing that we wanted to check is, so there are techniques that are trying to address this problem of compressing the memory inside LLMs, and we wanted to check whether these methods were doing any good, any progress in memory. And but these methods are usually based on different backbones, different architectures. So rather than comparing them, we re-implemented them. So we isolated all the components and all the techniques that they are applying, and we created a unified benchmark. Okay, before that, here is some statistics about the distribution of the different classes and also the distribution of the different recall times. This is what you find naturally in the data set that we started from. And this is also a qualitative example of the annotations. So you watch a video, this is the evidence, and then you're going to ask the question right after the evidence, what is the reason the person shook the bag, and then you ask it after 5 seconds, and I think this is going to be after a couple of minutes, and after a long time. And we check that the answer is still valid there. So this is what our annotations look like, and what the model is supposed to be able to do. So then to assess the state of the art, to compare the state of the art on this benchmark, we propose a unified framework. This is not something, I mean, new. It's like we surveyed the state of the art and we said, what are people doing? We try to re-implement this and to put everything in the same framework. So we have a system prompt that usually is something like, you are observing a video and describe what you see in the video, and you use this system prompt so that your video tokens, once they get inside your LLM, they are contextualized and they try to be descriptive. And these tokens are tokens that we save, and they are marked. They're usually called in the literature sync tokens, because there is evidence that you should not discard these tokens, but we also verify this claim. Then you have the streaming video, and for each frame that comes in, use a visual backbone plus a projector, and you append the token at the end of your KV cache. And then the part that you have in the middle is a mutable region where things can change. And now the idea is that you want to update this mutable region using some memory manager. You do an LLM, they call it forward pass, so that all these things attend to each other, so they are contextualized. And then you have a memory manager that tries to keep all this KV cache of a fixed size, okay? And these are the techniques that we found in the state of the art and that we investigate. So you have the mutable cache as input, and you do different things. You use token reducers, and we have different techniques. Intra-frame reduction, where we look inside one frame and we reduce things that are redundant inside the frame. And we do different things. We do pruning or merging mainly. And then you have inter-frame reduction, where you take consecutive frames and you drop whatever information is redundant, and you drop the older counterpart of the information. And then we have a residual overflow policy. So you use this to drop some tokens so that you are constrained to the budget. And if you still are over the budget, then you may discard in a FIFO way. So first in, first out, the things that are older, you discard them. Or you can do quantization, or you may not do quantization and offloading. So you save to disk whatever is overflowing. So this, what comes out when you read papers, they are trying to make these models streaming video understanding models. And the way it works is that you have an initial state where you have your system prompt, your mutable cache, and your new token. And then new tokens arrive, and you maybe prune some tokens, and you go like that. So you expand your cache, but at the end of pruning, you end up with the same pruned cache every time. Okay, I'm not going to read every single number of this table, but we try to be extensive there, but I'll present only some summary results. We tested different strategies, and some of these combinations intercept some state-of-the-art models. So these are some state-of-the-art configuration. We report accuracy across semantic categories, and as you can see from the colors, some categories are harder than others, and across temporal recalls. And of course, when you go to the right, you go to ultra-long, it gets harder. And the first thing that you see is that, of course, over time, so here we are averaging across classes of methods. So methods that are based on pruning, so on removing tokens, and methods that are based on merge. What we found out is that usually pruning works better than merging. This is probably because of an effect of some kind of, averaging effect that is losing details. So it's pruning tends to be better. And both pruning and merging are improving over the baseline. And interestingly, if you offload, you don't get a lot of benefits when you have instant short and short mid, but you get benefits towards the ultra long, which is reasonable. It's something that we would expect. Okay, these are the things I said. Also, in these box plots, you see the different classes of methods that are grouped by. There are two baselines, and then there are merge-based methods, pruning-based methods, and offloading-based methods. And as you can see, what happens is that pruning usually beats merge and offloading overall, but the gap is smaller in some cases. So for instance, for social, actually offloading tends to be slightly better. And the gap between pruning and merge is smaller in social and event. And also offloading, you can see it here, recovers ultra long and is competitive on social. So these are some insights that we get from this analysis. And I think this is a starting point to start evaluating memory in AI in a more consistent way than just reporting aggregate accuracy. Going to the second challenge, I want to show briefly a couple of works where we are trying to address another problem. And the idea is that we want to ground perception into external knowledge of the world. So what many works nowadays are doing, especially those using LLMs, is that you try to embed knowledge about the problem that you're trying to tackle in the weights of your network. So for instance, you train your network to recognize actions, and the knowledge about actions or procedures are inside your model. But this is not the way that that we function. So there is something that we do that is called cognitive offloading, where we use external media such as calendars or notes to ease our computation, to keep track of things. We don't just remember everything, and even if we are cooking something, we look at the recipe. We don't remember all the steps. This is something that that usually we are not doing while we are training our methods. And so we ask ourselves whether we can create and maintain structured representations of the world and inject them during the model, so that now the models are aware of these structured representations. And we did that in particular in procedural videos. In procedural videos, you have people performing activities that are procedural, so they have some kind of structure, like making a recipe. And one way to represent these structures is with the directed acyclic graph. There are different ways to represent them, but this tells you something about the constraints of the different steps. What are likely orders and what orders are not likely. And the first thing that we ask ourselves is whether we can extract this kind of structured representation directly from video. And the idea is that you have a set of videos and you want to obtain this kind of task graph. We have a work on that. I won't spend a lot of time on that, but this is a work from a couple of years ago where we created a differentiable model that can extract these graphs directly from video transcripts with a differentiable loss function. And the nice thing is that rather than using heuristics to extract these graphs, we are using a differentiable function. So this means that we do gradient descent into the graph. So for instance, for a task such as fix a flat tire, these are the different graphs that we iterate on during gradient descent, and in the end you settle on some lower complexity representation like this, where you see some parts of the representation which are these kind of preferential parts of the, general orderings of things that you should do, but you also have parallel paths that tell you that there are different variations in the way you can fix a tire. You don't have to follow strict order. So we want to encode this kind of information, like some things are impossible, other things are more or less likely. And what we ask ourselves is, can we use these graphs as a cognitive support? So can we give cognitive support to the models so that the models don't have to memorize this knowledge because we are giving this knowledge to them? And we consider as a task procedural planning, where you have a start visual state and a goal visual state, and you want to predict the steps that bring you to from the start visual state to the goal visual state. Okay, and the way you usually do this is that you basically put this inside a network, such as a transformer, and you predict the final plan. Instead, we ask, if I have a procedural knowledge graph, like the one that you saw before, can I inject this procedural knowledge graph inside the neural network so that the neural network is aware at training time of this procedural knowledge and can use the procedural knowledge at training time and so also at test time? And we use a simple Markov chain model where we ask the neural model to predict emission probabilities rather than posterior probabilities. And the way we constrain these to be emission probabilities rather than posterior probabilities is that after predicting these numbers, we inject these numbers into a differentiable Viterbi layer. So we take the Viterbi algorithm, we apply continuous relaxations, and then this differentiable Viterbi layer, we predict a plan, and we apply the loss function to the plan. So there are no weights inside here. The only thing that is changing is that these loss functions are mediated by the differentiable Viterbi layer. So the model knows at training time that it doesn't have to memorize the procedural knowledge graph because it will be available anyway during inference. And this is some form of cognitive offloading to the graph, which is available both at training and at inference. These are some results. So what we obtain is a method that we call Viterbi plan nets that works, depending on the dataset, it works on par with the current methods, but has less parameters. And we also show, and this makes sense because you need less parameters because you don't need to memorize all this procedural knowledge because you are exploiting the procedural knowledge at test time. And also we check sample efficiency. So what happens if you train with less data? And if you have the procedural knowledge, you are much more robust to lower quantity of data. So you are more sample efficiency. So you have good performance with fewer training examples. We also check what happens when you train for a given horizon. So for instance, you train to predict 6 steps, and then you test predicting 3 steps or 4 steps or 5 steps. So it should generalize, but what happens is that when you memorize your procedural knowledge, you are memorizing the procedural knowledge that you need for that horizon. Instead, when we provide the graph, we have we can generalize much better, and these are this stark difference that you see here. So we generalize better when the test horizon changes. And this is a qualitative example where we show that a base model that doesn't train with Viterbi tries to put the highest probability actions always on top. Instead, our model doesn't have to do that because the graph, there are this yellow arrow that you see here, will eventually correct whatever prediction. So it just needs to put the correct actions reasonably high in the ranking. It doesn't have to put them always first. And so this means the task is easier at training time. Okay. And so this is an easier cognitive task. Okay, I don't want to run too long, so I'll be brief on this one. This is another thing that we are recently exploring, and this is a collaboration with Lorenzo Torresani at Northeastern University and work done by Luigi while visiting his group. And another thing that we have been exploring is whether we can build specialized procedural models. So like models that specialize for procedural understanding. And the idea is we can give a video as input to a large language model or a VLM, and the VLM will predict the actions. So this is something that you can do, and the VLMs will predict something. Now I'll show some results of what happens in that case. We consider a dual input configuration, where in one case we use a Socratic approach where you translate video tokens to a description and use an LLM. In another case, you use a VLM. And if you try to test this, these are the results that you get. This is an open source model and 2 proprietary models. And as you can see, the top performance is well below 100%. So these models, again, they are powerful. It's not that they are not powerful enough, but they don't have enough context. They don't have the context of the activity. They don't have that kind of procedural knowledge. And we ask ourselves, can we inject that procedural knowledge inside these models? And now the problem is that there are different data sets that you can leverage for to inject this procedural knowledge, but most of them are clean and small, like small focused sets of data that have been carefully labeled. And then on the other hand, there are massive noisy video corpora, like for instance, how to 100 million, that have a lot of procedural knowledge inside. So how to 100 million is 100 million videos of people doing things, but they don't have very clean labels because they only have ASR, automatic speech recognition, transcription labels. And the idea is, can we use this noisy corpus to inject procedural knowledge? And of course, we already knew that if we would do supervised fine-tuning, that wouldn't help much because these models are very noisy. So the idea is, rather than doing supervised fine-tuning, can we use the noisy corpus, like how to 100 million, as a form of verification corpus? So can we use it to verify whether a predicted plan is a good plan or not? It's a little bit like when you align a model with reinforcement learning with human feedback. We are asking, but rather than asking human feedback, we ask how to 100 million whether the prediction is likely or not, and then we train with reinforcement learning. And this is how it works. So we do multiple rollouts of different candidates, and then we match the candidates to how to 100 million, and we look by using the history, there is the input history. We look for similar trajectories in how to 100 million, and then we obtain a subset of these trajectories. And after we obtain this subset, we do a high fidelity scoring that is a bit more expensive, and we score each of the rollouts. So the idea is that we assign a reward to the rollout. So if we find trajectories in how to 100 million that are similar to the trajectories that the LLM is predicting, then we are going to reward them positively. And then we apply GRPO. We also do some, we consider a baseline that it's the reward that you would get by just using the textual history without predicting anything. So this gives us a measure of how easy the task is. And so we subtract this baseline, and then we do some clipping to avoid too large or too small rewards, and we use GRPO. And this is what we get. So if you consider the base model without any training, we go for a smaller model, we have big improvements. We go from 1.5 to 9.1. So these are the boosts that we get. In domain cases where we are injecting some of this data from the same domain in the training procedure, and zero-shot cases where we are not looking at these data sets at training time, and these are the boosts that we're getting, especially in auto domain in zero-shot. And we also, of course, wanted to check whether our claim that this noisy data is not good for supervised fine-tuning was a good claim. So this is what happens when you have a best model and you perform supervised fine-tuning with clean labels for the dataset for which we have them. And what happens is that if you have a small model, it actually helps. For larger model, it doesn't help much. Especially in zero-shot, it doesn't work because whatever you are seeing at training time is outside of distribution. And then what happens if we do supervised fine-tuning with how to run the million that is noisy? This is actually worse than using the clean labels, and this is expected, so this is consistently worse. And our model is what works best, and even pre-training our model with the supervised fine-tuning actually leads to worse results, because the data of how to run the million is too noisy. I mean, it's too noisy to do supervised fine-tuning, but it's good enough just for verification and to train with reinforcement learning. The last thing that we show is that our model tends to have more diversity. So this is a measure of the diversity of the different predictions that you obtain. So if you do multiple rollouts, you obtain more diversity with our model. And also robustness to the amount of noise that you have in your supervised example. Supervised fine-tuning is kind of sensitive. If you give zero noise, it overfits. If you do too much noise, it underfits, and there is a sweet spot. And our model that is based on verification instead is usually flatter. You see the line is kind of less affected by this. Okay, and the third part of the talk is about how we should give a good feedback to the user. So now we have algorithms that can provide some kind of feedback. At the same time, intuitively, we know that we cannot just stop the user every 2 seconds to tell the user, oh, this is what you should do. So ideally, you should find a good moment to interrupt the user and find a good way to give feedback. And I selected just a couple of works. We've been working on action anticipation and mistake prediction for a while. But I think mistake detection is one of those tasks that you want to get right. So it's one of those feedback that is useful. You understand that the person is performing a mistake, and you give a hint. And in particular, in this work from last year, we try to see if we can detect mistakes without any supervision, because mistake prediction is one of those things where supervision, if you have supervised mistakes, you will overfit the distribution of the mistakes that have been performed. So we asked whether we can use gaze as a proxy of human behavior. So this is the idea. If you observe the gaze behavior of people performing an action and you average the gaze when the action is correct, you will find some consistency. If you average the gaze for wrong executions, you will find less consistency. And this is expected because there are a couple of good ways to do something, and errors are all unique. There are different ways to make mistakes. So we wanted to leverage that, and we come up with this idea. So we take as input both the video and the gaze, and then we ask, can we predict the gaze? Can we predict where the person is, what the person is looking at? And the idea is that if the person is doing something predictable, probably they're not making a mistake. If what they're doing is unpredictable, probably they're making a mistake. So what we do is that we train a model we call a gaze completion model to predict half of the gaze trajectory using the first half plus the video. The idea is that the first half of the trajectory is gonna do some kind of priming, so it's gonna tell this is the activity that the person is doing, this is the level of expertise, now complete what's happening, and if what is predicted diverge from what we are observing, then we're gonna say that this is a mistake, otherwise we say that this is correct. This is the idea. This is a qualitative example. So in the correct case, you see that the prediction is always around, the green one is the ground truth and the blue one is the prediction. The prediction is always around the ground truth, and in the mistake case, there are moments in which things get unpredictable because the person is dropping the script. These are some results on HoloAssist, where we consider 3 different levels of supervision. Full supervision, where we train models with mistakes annotated. And then we have unsupervised. The unsupervised case is a case in which at training time you don't know where the mistakes are. And one class is a case in which at training time you only see good execution. So that means you have some knowledge that your data does not contain mistakes. And interestingly, we test different models and different combinations, but interestingly, when you go one class, you get very close to the supervised case. And this is because this kind of task, if you use full supervision, you may overfit the distribution of errors that you see in your training set. Okay, the last thing I want to talk about is how to deliver help. And here is another benchmark where we're trying to fill a gap between the way that we are evaluating models and how we want them to behave. So of course, one way to obtain help with wearable devices is to connect them to a large language model. But the problem is that we are evaluating this large language model in a disembodied way. So we are letting these models watch a video and ask maybe what color is a screw. But the reality is that at some point, we want to ask very different questions. So we want to ask questions about what we're trying to achieve. And it's very hard to capture this kind of distribution of questions and answers that we want to get if we don't do this in the wild. At the same time, it's not straightforward how to do it in the wild, because in the wild, we want to have an LLM that is going there, answering questions, and we know that probably even the most sophisticated LLMs are not there yet. So how do you evaluate that? We drew inspiration from the wearable testing paradigm in a user interface. So the idea is that when you want to test a new function, so this is some illustration from the 80s. So the idea here was would be a listening typewriter a useful thing? And there was not, of course, speech to text at the time. And the idea is that before going there and develop the actual algorithm, you put a person in a room and you let this person pretend that they are the machine. So the person on the other room has this illusion that actually there is a machine doing that. So this is the idea of the Wizard's testing. And for those who read the Wizard's book, it should make perfect sense, because the Wizard of Oz pretends to be a wizard, but is just a regular person. Okay, so it's the same concept. And how do we implement that? The idea is that we have a person wearing AR glasses. We call this person a trainee. It's somebody who has not a lot of knowledge about the task that they are performing. And then in another room, there is an expert who's watching through the point of view of the person. The person is another view because we want the person to answer only from the egocentric perception of this person here. We don't want them to also look from a third person point of view. The two persons can talk, so there is streaming audio, and they can ask questions such as what is the first ingredient to take, and receive answers such as what they should do later. And we collect this kind of conversations, and we have in the end a multimodal data set, because we use our glasses where we have SLAM, IMU, transcripts, hand key points, eye gaze of the trainee, but also the eye gaze of the expert projected to the point of view of the trainee. And this constitutes a rich source of dialogues, of visual language data that we call Ego Extra, where we cover 50 hours of video, but we are extending that to around 100. There are natural conversation, 5 scenarios, and we obtain question-answer sets because it's a standard way to evaluate models, but the transcripts are there and are available, and I think they're a useful resource. We do the usual thing of asking LLMs to come up with questions, and then we refine with human validation using Amazon Mechanical Turk to be sure that the negatives and the questions themselves are meaningful. And then we also check with Amazon Mechanical Turk for grounding, and we discard all the questions that do not require the video to be answered, because we are interested in things that are multimodal. Then we analyze what we find in these questions, and we find something very different from what you usually see in question answering data sets. We have questions about procedure, so how to perform a given procedure, what's the next step, how to do something. Other questions are about clarification. Sometimes people just are not super sure, and so they ask, what should I do, or what is the color of something? So they ask for clarification. They know what to do, but they want some clarification. In other cases, they ask for comparison or choices. Should I use this or that? And then location or placement. Should I put this thing here? Or removal, attachment, insertion, and other, long tail classes that you see here. So we capture a very different distribution, and then we benchmark state-of-the-art models. We benchmark language-only models, and of course they are performing randomly. This is expected because they are not seeing the video, and we only consider grounded questions. And then we checked for video language models. What we see is that any model with the video is performing better, so video is needed, and there is a jump in performance. The top performer at the time, this was some time ago, was Lao One Vision. And also a sample human baseline obtains about 90%. So this means that the task is achievable. It's not 100% because some of these questions require some expert knowledge, but there is still a big gap to be filled. And I think this kind of resource is much different from what you see in usually video question answering data set. Okay, so this concludes the talk. Before closing, I think that these three challenges are something that will get us closer to the goal. At the same time, I think there are still lots of open questions. So, for instance, how do we build general purpose memory system? We were talking about this over lunch. I mean, it's an open problem. How do we evaluate memory exactly? And how do we create real efficient sensing? How do we decide when or what to sense? And also for knowledge grounding, how do we create systems that craft their own representation? Like rather than something static, let's imagine an AI system that creates a representation that is useful for it. And how do we perform general purpose cognitive offloading, which is not directly tied to the task? Or how do we learn when to intervene beyond understanding mistakes? And how do we evaluate whether the help that we're giving to the user is actually a useful help or not? And I think these are challenging questions and interesting questions, and I'm looking forward to see what the community is doing with that. And with that, I thank you for your attention and happy to answer questions.
If anyone have, so first of all, thanks for the excellent question. I think we learned really a lot, and also the interesting spread of all the top covering egocentric vision. So, anybody want to start with a question? I can first. Please.
So in all the work that you've presented, I think you were always missing action on the part of the AI system.
Mm-hmm.
So I, as a human, first of all, I have sort of an intention of what I want to sense, which my glasses might not know.
Yeah.
And the other thing is, I can move my head and sort of direct my senses towards what I want to sense. The glasses are sort of passive still. I mean, I move them around, but they don't know whether I will move my head over there and it sort of missed its chance to scan the QR code or something.
Right.
How to get around this?
Yeah, I mean, of course, this kind of paradigm is a paradigm in which the way that the AI is sensing the world still is very dependent on how the person is sensing the world. So there is a limit of what you can achieve. And in that sense, I mean, you could have, I remember there were works, I think, in the 2000s, so it was quite some time ago, on wearable robots, where you would wear a robot that would actually have some
actuation.
Yeah. There are some works on that, but it was a long time ago. So it was, but there was something also, I think, about SLAM. I mean, the idea that you are independent, like having a parrot, let's say, on your shoulder. I think that's an interesting direction. But I also think before getting to there, we still need to get so many things right about getting the most of what you are perceiving. Actually, the way that people move around is so, I mean, you do a lot, so many movements that, of course, you're gonna miss something, but the amount of information that you're capturing about the environment, even if you don't know it, it's huge. I remember there was a talk on privacy some years ago, where they were showing that you take, I don't know, 1 hour of a person going in their kitchen and doing things, and you can 3D reconstruct their home. So there was the privacy perspective there was, okay, we don't want our layout of our kitchen to be outside. But the amount of information that you still can leverage, even if you are not moving independently from the human, is already huge, and I think we are not leveraging that. But I mean, I do agree that there are some limitations there.
Thank you for the presentation, Professor. When you were mentioning about this active memory management, like it reminds me of like now in the codecs and in clouds, like they have the features of compacting this memory. So I'm just a user, like I don't know like what is the mechanism behind. Like, so I'm wondering is your techniques like applicable to the same problem, or they are just doing close attention, or they are just like going through all of the text again and write summarize by themselves? So yeah, can you briefly?
Yeah, is the question specific for like large language models or like
Yeah,
video language models?
Was there any differences, or like can they use the similar techniques with each other?
So I think I missed the first part of the question. So similar, like similar to what? So what is similar to what? Like was
So like in your presentation, you mentioned they are pruning their
yes,
their layout of these memory tokens.
yeah,
But what are these LLMs doing?
Right,
Are
right.
they working on the text, or they are also doing
right,
the
right, yeah,
text?
yeah. So the techniques I showed, they are proposed by works that are working with LLMs, with video language models, but it's basically LLMs. And so the idea there is that you do pruning or merging, but mostly pruning to remove tokens that are redundant. Like pruning works because if you think about how a transformer works, is like setting the attention for some tokens to 0. So everything keeps working once you pass everything through a softmax. So that's why pruning works better than merging probably. These are the things that they are doing, but there is another trend of research. There is like describing with text and then summarizing text. Like you take the video, you get captions from the video, and then you summarize the text, the captions that you got. And this works, but usually has limitations because it's much lower. So the idea of pruning and merging is that you put your tokens in the memory. You don't decode, so you don't have to predict text. You just change the input to your encoder in some sense. So that's why these methods tend to be, faster. But these are the two main things that you see in the literature. And somebody's starting to explore like using recurrent networks in the loop, which makes, I think, a lot of sense because they kind of have an explicit memory there inside.
Thank you.
I also have a quick question.
Yeah.
Just thinking out loud about those two projects you presented, where the first one is about memory, right? How to really efficiently remember what the model or what the video has shown, and the second one is about knowledge graph. I'm wondering, have you thought about like merging them in the sense that, given a video, we have some knowledge about general context, and then using the knowledge graph to guide the memory. Maybe then it's more like, okay, it can, like what you show, right? Like the intuition. Maybe it can find out already something that can be offloaded, or more suitable for offloading, and then the other part is more related to episodic pattern.
Yeah. I think that makes sense. We have not been exploring that. I've seen some works doing something like that for video understanding. Which has something to do with memory. That was not, let's say, marketed as memory, but more as like some form of retrieval augmented generation, which was based on graphs. But it does make sense to use graph to create a structured like memory of things and relationships between things. I think, that's interesting. Of course, whenever you use these structured representations, you have limitations. So you may want to have something to counterbalance the rigidity that you get from these structured representations. But yeah, that's something interesting, I think.
You were talking about like mistake detection or error detection.
Yes.
And what I understood was that you kind of track the user's eyes so that whenever they make a mistake, I guess their eyes kind of move around a bit so you can detect it. But then if the user isn't even aware that, I don't know, like they forgot to screw in one thing or something like that, would it not detect it?
Yeah. So we got some ablations in the paper, and let's say the intentionality of the mistakes and the skill level affects how informative this signal is, right? So there are some differences. So for instance, for novices, they tend to be maybe more, let's say, they may have more variability to begin with. So maybe you may detect something that is not a mistake as a mistake. And we do have some ablations that I don't have here in the slides. But I think the take-home message there was more than saying, this is a way to detect mistake. This is a signal that you can use to get, to get an idea of when the person might be confused. But it doesn't, it doesn't work, 100% of the times. Also, what we found is that by giving the first parts, the half trajectory of the gaze, we also tune a little bit for the level of expertise, because you have, if you have a lot of variability in the initial part, you can predict a lot of variability also in the ending part. So that helps a bit, but of course it doesn't predict all the cases.
In the very, like the first part of the talk was about sort of choosing between which sensors to sort of activate and
right
for wearable AR devices, etc. And you said that that you could actually extend the runtime to something like 8 hours on typically something that runs for 90 minutes or so, right?
Right.
So, like, you mean that when they're running SLAM on, like, that's what runs for 8 hours, or what?
So the idea was, the idea of the 8 hours was to answer the question, which budgets shall we set for these tasks? So when you evaluate these tasks, you usually set budgets. So you usually say, okay, I'm gonna restrict your computation to a given number of, in that case, it was milliwatts, right? So it's like a given number of millijoule per second, right? And so the point is that if you run something at 20 milliwatts on Ray-Ban glasses, you can run at 20 milliwatts for 16 hours. And reasonably, you are not doing just that. So we said, okay, if you stay at 20 milliwatts, then probably you run for 8 hours and you're using half of the budget for this task. And the task that we considered was temporal action segmentation. But then in the graph where we saw the curves, actually when you were at 20 milliwatts, nothing was working. So the reality is that we're not there. We have not been thinking in that way. And also, I think one point there was that of course, we will get larger batteries and so on and so forth, but we should keep in mind that these devices are constrained in the physical space. So you cannot put an infinite number of chips inside the limited space. So in the end, we have to think about budgets. So we have to think about algorithms that try not to, let's say, sense everything and try to route all these modalities so that they are constrained with budget. Okay, thanks.
Yeah, I have a question more on the sensing part and whether there are modalities that could be introduced, like ones that we're not using actually.
Yeah.
What is your opinion about that? If there is like new modalities that can be leveraged that might help better than what is existing?
Yeah, so I think once you use the modalities together in some sense, I think that some modalities that by themselves, maybe they are not super useful, they may become useful. So for instance, IMU is one of those that maybe with IMU alone, so we know that with IMU you can understand if a person is walking maybe, but you cannot understand if, you cannot distinguish whether a person is, I don't know, wiping a counter or cleaning a window maybe, right? But by using other modalities like, I don't know, audio, maybe you can differentiate between these. So yeah, maybe there are modalities that we are not thinking about that can be useful there. For instance, some things that we notice is that if you use a monochrome camera, you usually have less information than RGB because you don't have the color parts. But if you use a monochrome camera and a crop around the gaze, you usually get, the same performance of using RGB, because in the end, what you care about, it's also very similar to how we sense, right? So we are are like, we are very sensitive in where we're looking, and the rest is kind of blurred. So yeah, I mean, there might be modalities that maybe we are overlooking and things that are easy to catch that can be useful there.
If we don't have more questions, but I mean, we have the web page of Antonino, and that we can just look up. And then if you have any more questions on follow up, just feel free to shoot emails. Right, so yeah, then thanks Antonino again for giving the great talk. And
Thank you so much.
Thanks.
Thank you. Thank you.